thinking of the electron behaving like a wave, we know standing waves have certain areas where the value for the wave is positive, certain areas where the value for the wave is negative, and certain areas called nodes where the value of the wave is 0. Right? So if I have this guitar string, when I pluck it, depending on where I put my finger on the fret, when I pluck the guitar string, it makes a certain note, right? And the note changes if I change where I put my finger. And the note that I make depends on the distance between where the string began and where my finger is. That distance determines what frequency the string will vibrate at, and that determines the disruption of the air around the string, and that gets traveled to my ear with that specific frequency. So that's why I hear a certain note. There are also undertones or overtones to the note, right? So I hear the main note that string creates, but the overtones or undertones, whatever they're called, are based on other waves that can be created from that distance. But they're only, if I have a certain distance, there are only certain waves that can exist. Right? I'm not going to create a wave on this string when I have my finger here and the string has a certain length. When I pluck it, I'm not going to create a wave that has this wavelength. Right? The wave has to fit within that distance. So I can have a wave, the one that's shown here with 0 nodes, or I can have one that has 1 node, right? And the node is where the value of the wave crosses the axis, or the value of the wave is 0. Or I could create a wave with 3 nodes or 4 nodes, but I have to have an even number of nodes. So the more they looked at electrons in different experiments, the more they found that electrons behave like this. Electrons can really be kind of characterized as waves where only certain values are possible for the formula for that wave. And so you can't have a wave where n is equal to some fraction. Right? The wave is related to the number of nodes. You have to have a whole number value equal to the number of nodes. So Schrodinger elaborated on this idea and came up with a really nice, although quite complicated, equation, which we're not going to be dealing with because the math is beyond us, at least where we need to be in this class. But he created an equation for a wave. Okay, so this equation that we saw back here, this is a nice equation. It allows us to calculate the energy difference between energy levels based on whether it's the first, second, third level, etc. But this equation doesn't really tell us exactly what's happening with the electron. And so the Schrodinger equation is the best mathematical way to really get as much detail as we can about exactly what's happening with the electron. And as it turns out, that's still not that much detail about what's happening with the electron. So what we said at the beginning of class, and this comes back to that idea, is that the best model we have for how the electron actually behaves and where it's actually located is this cloudy region that comes from the Schrodinger equation. It comes from plugging values into the Schrodinger equation for n equals 1 or n equals 2, etc. And that equation, when you put it on a graph and you square the value for the equation, you get this picture. So it's a high-level math. It gives you a picture on a three-dimensional graph of this clouded region where the electron is located. And this matches with the experimental behavior of electrons. This is the best model we have because it's the only one that matches with all the behavior of electrons that we observed so far. Okay, so this is electron density. This is what an orbital is. So we're going to talk more about orbitals. But an orbital is a three-dimensional region where an electron is probably located. Right? So that's what we're talking about when we're talking about probability of finding an electron. That's what this is. This is the graph that shows the highest probable location. So we can't even determine where the electron is. We know it's maybe, so this is like n equals 1. Maybe it's in the first energy level, the ground state, close to the nucleus in a hydrogen atom. If it's in the ground state, we know it's energy. Right? We showed how that experiment and de Broglie were able to that formula was able to calculate the energy associated with n equals 1. We know the quantity of energy, but we don't know exactly where the electron is. So how could it be possible that the electron is in some clouded spherical region around the nucleus? We don't know exactly where it is, but we do know its energy. Shouldn't the energy be associated with this very specific distance between a positive and a negative? Based on the distance between the charges, we should be able to calculate the potential energy associated with that arrangement. Right. So we can calculate the energy for the electron. If it's in an energy level, we know it's in that level. We can excite it to another level, let it relax back down, and calculate the exact amount of energy associated with that. So we know that the energy levels have exact quantities of energy associated with them. But since the electron behaves like a wave, which results in this three-dimensional electron cloudiness, we don't know exactly where the electron is. So the result that we get from this is the electron behavior, that the electron behaves as if it's everywhere in the orbital at once. And that is because it's a wave and not a particle. If it were just behaving like a particle, it wouldn't be able to do this. It wouldn't be able to exhibit the behavior it has. But since it also behaves like a wave, we know waves can have positive values in some locations and negative values in other locations, and nodes in other locations, or values where the wave function is equal to 0. So since the electron can be described with the wave function, it behaves like a wave. It can be anywhere in this area at once. And so this density map shows the darker the color is the greater electron density, or the greater probability for the location of the electron. So the electron's everywhere in here, but more highly probably located in the areas of greatest density. Any questions about that? So if we take the Schrodinger formula and we plug in all the different possible quantum numbers, or all the different possible locations for the electrons, we get all these different shaped orbitals for different possible locations for where the electrons are located. So this one is spherical, the one we just saw. And this one is not spherical. This one has a good probability that the electron is either here or here. And what we have in the middle here is a node that exists on the XY plane. Right, so just like waves have nodes, the location of the electron, or the probable location of the electron, or the space occupied by this clouded negative region of electron density, can also have nodes. And so that means the electron can be here or here, but never in between. Again, that's a property of a wave, right? If I put a wave on a line, the wave function is here, the wave function is here, but the wave function is equal to 0 at the nodes. So this is another behavior of electrons that suggests they're more like waves than individual particles. If the electron was a particle and it got stuck up here moving around, it couldn't get to this lower area and move around without being in between. But a wave can. A wave can have a value of 0 in between two areas and have a positive value on either side. So we know the electron behaves like a wave because this model of where the electrons are located, or the electron density created by these shapes, it matches with the experimental data. So that leads to the best model we have, which is represented here by the Schrodinger. So let's see if I can make this a little faster so we can see these transitions happening more quickly. So look carefully at the blue cloudiness that's around here. So it starts off here, and then notice there's lots of different ways that it can move. So some have, some of these possibilities involve more, well, you can't see that, more region here and here. Some have like a clouded region around there. Some of these have like multiple layers of a clouded region. So that gives you a sense for when the electron is excited, it goes into a different clouded region that has its own specific three-dimensional shape. That's based on the Schrodinger equation. So that's the best behavior we have for electrons. So when the electron moves from one of these clouded regions to another clouded region, there's a specific quantity of energy associated with that. Okay, so it's still quantized, but the exact location of the electron is not known. It's behaving like a wave, so the electron is in this three-dimensional clouded region. And if it's everywhere in that region at once, that creates one average potential energy associated with that electron. So the quantity of energy when the electron moves from one energy level to another relates to the difference in the average energies for those electrons when they're in those clouded regions.